Yo, what's up, Science 10s? This is Mr. Walton coming at you from Lindsay Thurber. Today, we want to take a look at the motion of some objects. So as you can see, we got two cars here, and they both need to be able to get to the same spot, the same location. But because of the construction on one of the roads, we got some construction going on here, they're going to have to take different paths. They're not going to have to take different paths, but they want to get there the fastest. And so the blue car is going to travel along 91st Street through the construction. And then the red car is going to take 51st Ave and go up around the construction. And we're going to see which car can get there the quickest or first. So let's watch their motion as they travel around. And I'm going to ask you some questions here in a little bit. Oh, that was interesting. That was okay. All right. So I got some questions for you. Which car traveled or had the greatest distance? All right. And which car had the greatest displacement? Now, if you don't know what those two words are, I suppose we should probably go ahead and define them. So that's what we're going to do right now, and we'll come back to this here in a little bit. Okay, so we're talking about scalars and vectors, and it's totally okay if you've never heard of either of those two terms before, scalars or vectors. But that's the idea of distance versus displacement. Now, scalars are values that do not have a directional component. So as an example, I traveled 53 meters, but you don't tell me which direction you travel. You're just saying, I went this distance. Or that's like saying, when I was driving down the highway, I was going a speed of 60 kilometers per hour. And so hopefully you notice that they've got values attached to them. They've got numbers, so 53 meters or 60 kilometers an hour, but they don't actually have a directional component. So that's what a vector is. A vector is a value that does, vectors are values, that do have a directional component. So as an example, I could say that I went 53 meters east. And that's what the E, capital E in the square brackets, it just means east. Okay, so I could say that I went 53 meters east, or I could say I went 60 kilometers an hour north. Or, any other combination of direction. So that's the difference between a scalar and a vector. These scalars don't have any directional component, but these vectors do. And so what you often see the vectors are written as like a letter with an arrow above it, where scalars aren't. So one of these two things means velocity, and one of these two things means speed. One of these two things means distance, and one of these two things means displacement. And so hopefully you can tell that the vector is the one listed with the arrow above it. Okay, no problem. So what we want to do is we want to see if the following units are considered scalars or vectors. And we're going to look at page 5 of our data booklet. So here we got page 5 of our data booklet, and when I'm going through here, page 5 of your data booklet lists a bunch of formulas and a bunch of units and things like that. So when I look here, I see that we've got a bunch of letters or variables, and they stand for certain things. So a lowercase v with no arrow on top of it is average speed, and average speed is typically measured in meters per second. Those are the IUPAC units for average speed, meters per second. Now, the difference between speed and velocity is that velocity has that arrow above it. So what does that mean? Which one of these is a scalar and which one of these is a vector? Yeah, you got it. So speed is a scalar because it's got no directional component to it. And then velocity is a vector because it's got a directional component. It's got that arrow above it. And so we can take a look at this list and we can use it to be able to identify the difference between scalars and vectors. Okay, so let's go back. Are the following units considered scalars or vector units? So speed or velocity. We already know speed, right, is v with no arrow, and then velocity is a v with an arrow. So that's a scalar, and that's a vector. Mass. Let's take a look at mass here for a second. So we'll go look at mass. Mass is m, and it's measured in kilograms. M with no direction. Well, hopefully that makes sense. So it's a scalar. That mass can't have a direction. You can't have, like, my body mass can't be 70 kilograms north. That doesn't make any sense. That doesn't make sense, right? It's nonsensical. I don't even know what other word to use to describe that. Okay, let's keep going. Force and energy. When I take a look at force here is written with an F and no arrow. But I want to be very clear. Forces can be vectors, okay? So we could say F, or we could say F with an arrow above it. So they could be a vector or a scalar, okay? The term force can be used for both of those things. Let's take a look at, what was the next one? Energy. Work, okay. E is energy, so gravitational potential energy measured in joules. I don't see any arrow above it. Kinetic energy, I don't see any arrow above it, so we're going to say this E with no arrow above it, so that's a scalar. Time can't elapse, 10 seconds north. You can travel north in 10 seconds, but time didn't go north. Do you know what I mean? Time doesn't, if one person's traveling north and another person's traveling south, it's not like time is traveling north and time is traveling south for that person. Time is just moving forward. It's just elapsing, right? So time, t, is going to be a scalar. Now here we go. This is what today is all about. Distance versus displacement. When I look at this, distance, no arrow. Distance is a scalar. So we can use d or delta d. So that's a scalar. And then displacement with an arrow on top, that is a vector. And then lastly, acceleration. Acceleration is with an arrow on top. I mean, we can talk about either or, okay? We could say A, or we could say A with an arrow, so it can be a scalar or a vector. The word acceleration can be used for both, so that's okay. That's no problem. Whatever, it's all good. Okay, we're going to go ahead and move on. So distance, as you just saw, distance is a scalar quantity, which refers to how much ground an object has covered during its motion. So that's like, if you went from here to here, that's how much ground did you cover the entire time, right? So you add up all the individual distances and you figure out how much did you travel. Displacement is a vector quantity. So anytime we need a vector quantity, that means we need a direction along with a number. So it's a vector quantity that refers to how far out of place the object is. That doesn't make sense. How far out of place an object is. An object, Walton. Come on, man. It is the object's change in position. So if I went from here to here, a lot like I did up here, okay? Yeah, I know I went up and over and down and over and up and over and down again. But all I care about is I went from here, start, to here, finish. I don't care how I did it. I went from here to here. And so the displacement, you don't look at anything in the middle. You can, okay, and what we're going to talk about, it's a little complicated, but all you really care about is from beginning to end, what happened. That's what we care about. Distance is how much ground did you cover, and displacement is from start to finish, how far did you go. So what we're going to do, let's go back and let's try and see what the distance and the displacement of each of the cars in the example was earlier. So when we were watching that video, the blue car, it went straight from here all the way to there. So it's because it didn't do multiple movements, it just kind of did one movement, right? It went straight from here to there. Its distance and its displacement are the same thing, okay? It went 1.3 kilometers. For the blue car, the distance, right, D with no arrow, so it went 1.3 kilometers. That's pretty easy, no problem. Its displacement was 1.3 kilometers, and we have to be very specific about what direction did it go. So it started at the bottom and went to the top. So what direction was it traveling? It was traveling north. Okay, so that was easy with the blue cars. No problem, whatever. So let's go check out the red car. So the red car, it ended up traveling from here all the way over, and then all the way up, and then all the way over, okay? And then it finally ended up here. So from start to finish. So what we're going to do is we're going to try and see what was its total distance. Well, it went 1.24 kilometers, 1.24 kilometers. And then it traveled up. Well, hopefully you know this about, rectangles, is that if I go up, this distance up is the same as this distance is. So the red car went another 1.3 kilometers. And then it went back. It backtracked on the 63rd Ave. So it went another 1.24 kilometers, 1.24 kilometers. So when we put all of those things together, we're going to get a value of 3.78 kilometers. So that was the total distance. So the distance of the red car was 3.78 kilometers. That's how much ground it covered. But let's think about what happened. I'm just going to draw another picture. It started here, went that way, and then that way. And so really, from start to finish, that red car just went from here to here. It went that far. That was the displacement. And so the red car's displacement is going to be the same as the blue cars. The blue car's displacement, they started and finished in the exact same spots. And so the displacement of the red car is also going to be 1.30 kilometers north. And so which of these cars covered more ground? Well, the red car did. But which of these cars had the greatest displacement? That was the question, one of the questions I asked you earlier. Which of these cars had the greatest displacement? Well, they had the same displacement. It doesn't matter how you get there. Displacement only cares about where did you start and where did you end up. Now, we can use a bunch of different ways to figure out displacement. Displacement is a little difficult for some people, so we're going to go through some examples here in a second. Okay, so there's kind of two common methods of indicating or reporting a direction for a vector. And the first one is kind of the north, south, east, west method. And that's you indicate the direction by saying, bracket N for north, S for southeast, E for east, and W for west. And that's all well and good. Sure, no problem. But the second kind of more important way of doing it is by using a positive and negative. And so if a scenario deals with only north and south, or only east-west, or only up-down, or only left-right, or only blah, 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 we can define one of these directions to be positive and the other direction to be negative. And this makes adding and subtracting the vectors much easier. Now, a really super common way of being able to kind of indicate the direction for people is that we always say north is positive and south is negative, just up, down, right? And we always say east is positive and west is negative. So that's kind of right, left. And so this matches, I don't know if you remember, but this matches the Cartesian plane. So the system of XY coordinates. So we kind of say that the east-west is like our x-axis. There's the positive x and negative x. And then we kind of say north-south is the y-axis, so positive y and negative y. So it's just for the math people, that's a way of for us to be able to remember that. And so this is super nice because if we only have an object traveling in like two directions or whatever, then all we have to do is we just have to say, okay, if I went this way by 2 kilometers and then I went that way by 3 kilometers, that's like saying positive 2 kilometers and negative 3 kilometers. When we add them up together, that's like saying, well, our displacement was negative 1 kilometer when we add them up, because we went more negative than we did positive. At least that's the idea behind it. Okay, perfect. So we're going to do a couple examples. So displacement example 1. A physics teacher walks 4 meters east, 2 meters south, 4 meters west, and then finally 2 meters north. Draw a diagram illustrating this motion. So I don't know, I'm going to put just a dot right in the center, and that's going to be our start position. And so we went 4 meters east, no problem, 4 meters east. And so I'm going to indicate the length of the arrow is going to be 4 kind of units long, and it represents 4 meters in the east direction because I'm drawing it pointing east. Then from there, I go 2 meters south. So from the end of the arrow, we go 2 meters south. And we want our arrow to be 2 of these units. Do you know what I mean? So if this was 2 meters from here to here, we want it to be the same length. So this represents 2 meters south. And then from the end of that arrow, I went 4 meters. Holy, that's terrible. 4 meters. So 1, 2, 3, 4 meters west. And then from there, I went 1, 2 meters. I'm terrible at drawing arrows, sorry. And then we went 2 meters north. Okay, no problem. So there's our diagram. We're using arrows, and we just started somewhere, and then we went around, and we just drew what kind of directions we went and how far we went. And so remember, it's important to understand that if this means 3 meters, 1, 2, 3, no, sorry. So 1, 2, 3, then this has to mean 2 meters. Okay, so it's the length of the arrow indicates the magnitude of the vector, and then whichever way you point it, that means the direction. So we drew a diagram. What is the displacement? Well, the displacement is all of these vectors added up. Okay, and so let's think about this. I went 4 meters east, but then eventually I went 4 meters west. So my displacement, so 4 meters in the east direction plus 4 meters in the west direction. Well, those are opposites, right? That's like positive and negative, and so they cancel out with each other. And so that we kind of really didn't go anywhere, at least with the east-west. Okay. And then where did we go? We went 2 meters south, but we also went 2 meters north. And hopefully you understand that it doesn't matter what order I put these in, because again, south and north are opposite, and they're the same size, and they just cancel each other out. So what was the displacement? Well, the displacement was 0. It was 0 meters, and I can't put a direction because 0 has no direction. You can't draw an arrow, 0 meters long. It just doesn't work. So I don't know. Hopefully that made sense. Let me know if it didn't make sense. Just comment on the video or email me or something like that. Okay. Use the diagram to determine the resulting displacement and the distance traveled by the skier during these 3 minutes. So we start out here. This is our start. And I know it's start because it's time equals 0 minutes. We're also labeling it as A. So there's the start. So what do? We went right. Sorry, I was going to say left there for a second. That's a long L. We went right all the way to t equals 1 minute. That's B over there. So how far did we go? We went 40 plus 100 plus 40. So okay, all right. So from A to B, from here to here. Oh man, I'm bad at drawing arrows today. Whoops, sorry. So we went 180 meters, and I'm going to say that's to the east. Hopefully that's okay. And then from B to D, from B to C, because that's the next time, 2 minutes, we went from here to here. That was 140 meters west. Oh man, I'm going to erase that. That's terrible. What is going on there? Whoa. I'm going to erase that. Oh man, nothing good is happening in there. Nothing good is happening. Okay. So I went from there to there. That's still not good. 140 meters west. Perfect. And then from C to D, we went 100 meters east. So let's do this. Our distance is the total of all the ground that we covered. So let's take all of these distances, all of these tiny little amounts that we covered, and let's add them up, but let's add them all up and ignore the direction, because D, like distance, has no arrow above it, so we just ignore the direction. We went 180 meters, that's how far we went first, and then we went 140 meters, and then we went another 100 meters. So if my math holds right, 420 meters, no problem. Okay. So now let's figure out what the displacement was. And the displacement's going to be different. Hopefully that makes sense, because we're changing our direction here. So we went 180 meters east. Well, what's east? Is that positive or negative? That's positive, right? What's 140 meters west? That's in a negative direction, right? And then 100 meters east, that's again in a positive direction. Let's add all this up. So we went positive 180 meters. That means in the east direction, right? I'm just using a different label here. That's all I'm doing. So this just means we went in the east direction. I'm switching between my positive and the positive negative and the northeast southwest. So we went positive 180 meters and then we went back. So that's a negative direction, 140 meters. And then we went to east again, or to the right. So positive 100 meters. And if I add all this up, 180 minus 140 is 40, plus 100, so that's 140 meters in the positive direction. Okay, so remember that negative, all that means is we went west. The positive, all that means is we went east. And our resulting vector is positive, so that just means we ended up east, right? Or 140 meters east. That's all that means. That's a terrible bracket. Holy guacamole, that's a terrible bracket. So what I want you to do is I want you to try the questions on the next page. There's not a whole heck of a lot of questions here. There's not a ton of questions. And so I think there's only 3 or 4 questions. So use this information to answer questions 1 and 2. Use this information to answer question 3. And then check out the key if you have any problems. Check out the key or the filled in notes if you have any questions or anything like that. Come talk to me in the office hours. I'm going to go ahead and admit it. So far, I haven't had a single person talk to me in my office hours so far this week. So if you're struggling, if you're not understanding this information, just log on, click on the link in the instructions for today, and log on and ask me a question, because odds are there isn't going to be anybody else there. You don't have to be afraid that you're going to embarrass yourself in front of other people, because you're probably going to be the only person there. And you get to ask me a question directly. If you're still nervous, email me and we can set up a time to chat privately. We just you and I can chat and we can figure things out, and that way you don't have to worry about maybe asking a question in front of other people or something like that. Let me know how it goes. I would love to hear from you. Otherwise, have a great day. Good luck. Have fun.